Okay. So recall what the rule was. Recall if limit x goes to a of f of x is equal to 0 or infinite. Okay, let me write. And limit f of x, g of x as x goes to, okay. I was trying to write both of them in one sentence, but okay, let's write it in two sentences. Then this information does not determine the limit x goes to a of f of x over g of x. Okay? So we summarize this. We write limit f of x over g of x as x goes to a is equal to 0 over 0 in parentheses to summarize the above. Okay. Similarly, if limit x goes to infinity, again, let's take a f of x is equal to infinite and limit g of x as x goes to a is infinite. We write limit x goes to a f of x over g of x is infinity over infinity inside parentheses. Okay, so the same story. This is just a symbol. So here, a can be in R, or a can be plus or minus infinite. Okay? So there are proofs of this thing, but we are skipping the proof because we are not going to use the ideas of the proof later in the problems. That's how we planned the course. Okay. So last time we showed how this works when we are in this case where f is continuous and also takes the value 0. Okay. So let us skip that. Here, one note is sometimes, okay, so before I give the note, let me give you what the rule was. So recall that in this case, recall that in these indeterminate cases, the rule suggests a way to find the limit. Okay, so the rule says that the limit of the ratios is equal to limit of the ratios of the derivatives. Okay, so if limit x goes to a of f of x over g of x is equal to 0 over 0 in parentheses or infinity over infinity in parentheses, then limit x goes to a of f of x over g of x equals limit x goes to a f prime x over g prime x. If the limit, if the left, this is right? If the right-hand side limit exists. Okay, so you look at the ratio of these. So note, if you look at the limit of the derivatives, f prime x over g prime x, it's also of the form like this or like this, in which case we apply the above rule once more. Okay? So you keep taking the ratios of the derivatives until you come to a case where you don't have this or this. Okay? So at that stage, you don't apply the L'Hopital's rule because it's meaningless. At that point, if you are lucky, you calculate the limit in some other way. Okay, so this is what we did last time. So, and we calculated some crucial limits. Using this rule, we calculated some crucial, how do you write crucial at 8 o'clock in the morning? Crucial limits. Okay. So, for example, we are interested, so we have polynomials, logarithms, and exponential. Okay, so these are the things that generally show up very often. How do they fight with each other? Okay, so we had limit x goes to 0 of x to the alpha ln x to the beta is equal to 0 for all alpha beta positive. Okay, so here, of course, the interesting case will be when alpha is very, very small, beta is very, very large. So they fight against each other. Okay, and polynomials always win. And we also had, so we had this, and we also have limit x goes to infinity in this case, e to the x over x to the n. Okay, so this is equal to infinite for all n positive. Okay, so this one says let's go to infinite, and 1 over this says let's go to 0. They are fighting. Okay, so no matter how large you make this n, this guy will win because both of them are because of the L'Hopital's rule. You are taking derivatives. Once you take the derivative of this thing, okay, it loses a power, but by chain rule, inside gives an extra power of x, which feeds x to the alpha. So x to the alpha remains the same throughout the calculation. Okay, here we write this divided by 1 over x to the alpha. Okay, and here the same thing. You keep taking the derivative of this, nothing happens to it. But as you apply L'Hopital, this guy loses power. So eventually it disappears and this wins. Okay, so these were the two things that we have to know. And other things are, other note is that sometimes in L'Hopital there is a chunk which doesn't contribute to the indeterminacy. Okay, you can blindly start taking the derivative of that, but of course it helps if you so another note is this. So sometimes there are parts in an indeterminate limit which do not contribute to the indeterminacy. Okay, in that case, in that case, treat them separately. Okay, so there was an example. So let's do one example. So limit x goes to 0 of, we had something like this, secant square x tangent x over x, for example, okay, just to make life easier. Okay, so you see that derivative limit as x goes to 0 of secant square x is 1. It's not giving 0. 0 is being contributed by this. So indeterminacy lives here. But if you look at this blindly, the numerator goes to 0, the denominator goes to 0. So you can take limits of both sides. You will have a crowded expression on the top. Things will work out. You'll get the correct limit. But you are risking making a mistake by taking too many calculations. So here, secant square x is not contributing to the indeterminacy. So I see this thing as limit x goes to 0 of secant square x times limit x goes to 0 of, well, actually, I can here write tangent x over x. Okay. In fact, you can write tangent x also as sine x over cosine x, so it comes to make this secant cube, but let's not get that complicated. We are trying to do this the simplest way. Okay, now here, the limit of this is 1 times, here now we apply L'Hopital, limit x goes to 0. Derivative of this is secant square x, derivative of this is 1. So you see that applying L'Hopital was easy. So this is now 1, so everything is 1. Okay? So as opposed to taking the derivative of the whole thing. Okay? So this is another thing that's useful in applying L'Hopital. And another thing is, of course, you don't apply L'Hopital when it is not the case, but sometimes you start taking the derivative and you just don't stop and you keep going until you get a meaningless expression. Okay? So the important thing in these things is to know when to apply L'Hopital. If you don't have indeterminacies, then L'Hopital does not apply. Okay, so what else? Okay, the other thing that we started, so we stopped here last time. We have indeterminate powers. Okay, so we can apply L'Hopital's rule to indeterminate powers. Okay, so these powers are, you have f of x to the power g of x, and you want to take the limit of this as x goes to some place. Okay, so it can be of the form, so again, let me use this notation. So let's see, both of them go to 0. Okay, so f of x going to 0 says, okay, 0 to anything, any power will be 0. We are talking about positive power. Okay, so roughly speaking. So because of this, we expect the limit to be 0, but this is taking to the 0th power eventually. 0th power of something is 1, so they don't agree. Okay, they say, one of them says, let's make the limit 0, the other one says, let's make the limit 1. So they are fighting. That's what we mean by indeterminacy. Or it can be, let me see these things, infinity over 0. So again, clearly they are fighting. Another thing is 1 to infinity. Okay, so in this case, what is indeterminate is, of course, f of x. If f of x is identically equal to 1, they are not fighting. But f of x is going to 1 in the limit, and in general, it is different than 1. If you have a number different than 1, and if you are raising it to higher powers, it either goes to infinity or to 0. If it is less than 1, taking successive powers makes it 0 eventually. Okay, so that's why they are fighting here. So in these cases, we use logarithm. Okay, so that's why logarithm survived. The main purpose of logarithm was to make multiplication easy. Multiplication by hand was made easy by logarithm, using tables. But then, since we don't need it anymore, we could just throw logarithm. There were lots of other techniques in calculation, none of which we teach you today because we have calculators. Taking square root, for example, do you know how to take square root of a, say, 6-digit number by hand? Okay, we learned those things because there are algorithms to do this. You find the square root up to any digit of precision you want by hand. Okay, then you have calculators. Now, who needs those techniques? So the same thing would be the fate of logarithm, but logarithm survived because we are using it for other technical reasons now. For example, in these cases, logarithm serves the purpose of bringing this g down. Okay, when g is down, now we are in the case of L'Hopital's rule. Okay, so two things are fighting. They are multiplying each other. So multiplication can be also considered as division. Okay, if a is multiplying, then 1 over a is dividing. Okay, so that's where L'Hopital comes in. Okay, so here we use log function or write ln. Okay, so I use these things interchangeably because I forget whether I am in complex calculus or real calculus. Here we use log function to bring the situation to the interest of L'Hopital. Okay, so if y is equal to f of x, g of x, okay, then ln y is equal to g of x times ln f of x. Okay, of course, for this thing to make sense, we must make sure that f of x is always positive. But in this case, it will be positive most of the time. And here we expect that f of x is positive and going down to 0. Okay. Then we are interested in the limit of y, but first we start limit as x goes to a of ln of y. Okay, so this is limit of x goes to a of g of x ln f of x. Okay, so suppose now we calculate this. So suppose we calculate this using L'Hopital and other things. Okay, because there is hope that we can calculate this, because all of our rules apply when the parameter x is on the same line. Okay, if something is if x is in the exponent, we don't have any rules for them, but then logarithm takes it down and then we beat him. Okay, so suppose this limit is L. Then here we observe the following, that ln is continuous. Of course, you don't need to write these things in detail when you are doing a calculation. I'm explaining why those things work. Continuous means that the limit goes inside ln of limit as x goes to a of y. So this is the definition of a continuous function. Okay, the value of the function at the limit is the limit of the function. Okay, and now this thing is equal to L. Okay, so we take it here. We know that this is equal to L. Now take exponent of, now take exp of both sides. Okay, from here. So you get limit x goes to a y. Remember, ln and exponentiation are inverses, so it kills this, and this becomes e to the l. Okay, so this is how we handle problems of this type. Okay. So let's see, and for these things we did a few calculations, so let me remind some of them and then start doing some new problems. Okay. So we did this one, limit x goes to 0 from the right, x to the power x. Okay, so it's of this form, 0 over 0. X is going to 0 from above, so x is always positive. So we can talk about ln of x. Okay, so for this thing, we set y equals x to the power x, then ln y is x ln x. Now we take the limit x goes to 0 from the right of ln y is equal to limit x goes to 0 from the right x ln x. Okay, so this is one of the limits that we know by heart. Okay, this x always beats a logarithm, so x says let's go to 0, everybody goes to 0. Okay, now applying that thing here, therefore we have y limit of x going to 0, y is e to the 0. Okay, so let me write just for x 0, this is 1. Okay, so the limit was 1. Okay. So another thing is this. So we'll do this more generally in a minute. Okay, so maybe I do this and then the other one. So limit x goes to infinity, 1 plus 1 over x to the power x. To the power x. Okay, so this is of the form 1 to the infinity. Okay, so remember that this is indeterminate form 1 to infinity. Inside, it's going to 1. The power is going to infinity, but inside, you see, is always larger than 1. Okay, so since inside is larger than 1, and I'm taking larger and larger powers, so this thing may go to infinity. Okay, so that's one of the mistakes we sometimes do while we are thinking about a limit. If you do this thing step by step, okay, so the inside is always larger than 1. I'm taking infinite powers. I'm taking larger powers, so the limit is infinite. So this is something that comes to mind. But the mistake we are making, the fact that we are overlooking is that while this is larger than 1 and becoming smaller, then this is going to infinity. This is becoming larger. So both things are happening at the same time. Or you can commit the same mistake by saying that x is going to infinity, so this thing becomes 0. So this inside is 1. I take any power, the limit is 1. Okay? So again, while you are considering the limit of this thing, by mistake we think that this x is staying here and just watching what is happening. Okay? So that's not the case. Both of these things are increasing at the same time, and we have to understand how they are fighting in between. Okay, so that's one thing to avoid in trying to understand limits. You can't put your finger on one of the parameters and check its effect while the parameter also appears somewhere else. Okay, it doesn't just sit there. Okay, so we apply the same thing here. We say let y equals 1 plus 1 over x to the power x, then ln y is equal to x ln 1 plus 1 over x. And since, okay, we check here, when x goes to infinity, this is ln 1, this is 0. I'm multiplying it with infinity. Okay, so they are fighting. I write this thing as ln 1 plus 1 over x over 1 over x. Okay, now thinking about the limit as x goes to infinity, this goes to 0, this goes to 0. Okay, so limit as x goes to infinity of ln y is equal to limit x goes to 0 of ln 1 plus 1 over x over 1 over x. So this is 0 over 0 indeterminate case. So we apply L'Hopital. So this is limit x goes to 0, x goes to infinity. Okay, so this is 0 over 0. So the derivative of this is 1 over 1 plus 1 over x times the derivative of inside, which is minus 1 over x squared, divided by the derivative of this, which is minus 1 over x squared. Okay, so I cancel these things, and I have this limit. Now I check at this point if it is an indeterminate form or not. Okay, when x goes to infinity, this goes to 0, so the whole thing goes to 1 over 1. The limit is 1. Okay, so you don't start taking limits after this. So this limit is well determined, and it is 1. Okay, so what did we find? So we found, so if you take this thing now, ln is continuous, blah, blah, ln of limit x goes to infinity y is equal to 1. So you take the exponent of both sides, limit x goes to infinity is equal to e to the power 1, e. Okay? Well, limit of y is e. Okay, so this gives us an idea about calculating the limit of e to the x. Okay, so I managed to. So this is, you see, e to the power 1. Where did this 1 come from? If I can detect that, I can calculate e to the x as a limit of something, and well, it's sometimes useful, and most of all, it is fun. So how that works is the following. It turns out that this one comes from the one here. If I put a parameter here, that parameter will show up. Why? It will show up here, right? I take the derivative of inside. If I have a parameter here, it will be minus that parameter over x squared. I don't have a parameter here, so these will cancel. When I cancel, I'll have just t here, and the limit will be t. This will be e to the t. So how you do this is the following. So this is the following is more famous way of calculating this. So calculate, let x be any real number, find limit as n goes to infinity. In this case, n is an integer. So this is more suitable to doing calculations with computer, etc. Okay, so it is exactly like the previous one, except that here you do it step by step. Every time you calculate this with the with an integer. So what happens is that you can do this recursively. You start with 1 plus x, then you multiply, then you consider 1 plus x over 2 squared. Okay, so you keep doing these things one by, and this thing converges to a number, even though the convergence is very slow. So again, let us do this thing, 1 plus x over n to the power n. So ln y is n ln 1 plus x over n. Okay, so this is of the form ln 1 plus x over n divided by 1 over n. Now I can talk about the limit. Limit as n goes to infinity of ln y, which I know is equal to ln of limit n goes to infinity of y. And this is the thing that I'm trying to calculate. Okay, okay, now this thing is equal to limit n goes to infinity of this part, ln 1 plus x over n divided by 1 over n. Okay, here n is the parameter. So when we apply L'Hopital, we are treating n as a continuous parameter. So this is again one of those boring, obvious-looking theorems we proved, or at least mentioned when we were doing limits. If you are taking limit of some of a sequence as n goes to infinity, then if the function can make sense when you substitute x, a real parameter, instead of the integer, then the limits will be the same whether x as n goes to infinity or x goes to infinity. Okay, so that's obvious, but we had to mention it at least once so that now we use it here. Okay, so here we use L'Hopital. Okay, so treat n as a real parameter. Okay, so limit n goes to infinity, derivative of this with respect to n, 1 plus x over n times derivative of this is minus x over n square, and this is minus 1 over n square. So when we cancel these things, okay, let's see, n squares cancel, minuses cancel. And what remains is, okay, let me just, for the fun of it, write it once more. Limit n goes to infinity of x over 1 plus x over n. Okay, so here we see that there is no indeterminacy. Okay, as n goes to infinity, this goes to x. Okay, so we know that now this is equal to x. ln of something is equal to x, so that something is e to the x. Okay, so we have limit n goes to infinity of y is equal to e to the x. Okay, so you can try this with the computer and see how this thing, how this approximates e to the x. Okay, so what other things? Okay, so I have this and this. Okay, so we have time to do all these calculations. So what's the number? Let me follow the numbers. 4. Okay, a typical case, limit as x goes to 0, sine x minus x over x cubed. Okay, so next semester you'll look at this and immediately say 1 over 3 minus 1 over 3 factorial. Okay, because that's how sine x is written. You sine x starts with, okay, so next semester, we will know that sine x is equal to x minus x cubed over 3 factorial plus x 5 over 5 factorial minus, okay, so you see the pattern. You have only odd powers divided by factorial of the power with alternating signs. You subtract x from this, so you subtract this, what you have is this. Now you are dividing it by x cubed, so this x cubed cancels, but all of those things, after you cancel x cubed, will have an extra x in it. When x goes to 0, they will all vanish. So what will remain is minus 1 over 3 factorial. Okay? So this is the easier way of doing calculating indeterminate limits when you realize that you have to take lots of derivatives and the functions are complicated. Okay? But with these things, we don't need this. So here we can use L'Hopital because this is 0 over 0. Limit x goes to 0. L'Hopital kills only one power here, so you need 3 applications of L'Hopitals. In this method, as you write this, so here the trick is writing this, then you cancel it. You see the effect of 3 successive L'Hopitals in one step. Okay, so here we are expecting to do this 3 times. Derivative of sine x is cosine x minus 1 over 3x squared. We again check if this is 0 over 0. Cosine x goes to 1, so this is 1 minus 1, 0, 0 over 0. So we apply L'Hopital once more. Limit x goes to 0. Derivative of this is minus sine x. This is constant. This is 6x. Okay, so here you can write the limit immediately because we know the limit of sine x over x. But now that we are on to L'Hopital, let's hit this with L'Hopital once more. Okay, so again, L'Hopital. Limit x goes to 0. Derivative of sine is cosine, and I have this minus thing, cosine x over 6. Okay. Now, if you apply L'Hopital once more, you will get sine x over 0, and then you will say the limit is infinite. Okay, but of course, the limit is not infinite because L'Hopital is not applicable in this case. Okay? Nobody prevents you from applying L'Hopital, but to get the correct result after you apply L'Hopital, you must check if L'Hopital's rule is promising you something. Okay? So this is not an indeterminate form. As x goes to 0, this goes to minus 1, this goes to 6. So we already have the number minus 1 over 6, okay, which is minus 1 over 3 factorial. Okay, here we have a horrible calculation. Maybe I can skip this. Okay. Let's see if we have some fun things here. Okay, so we have things like this. Again, let me do a power, indeterminate power. So limit x goes to 0 from the right or from the left, doesn't matter in this case. I have cosine x to the power 1 over x squared. Okay. So the power exponent goes to infinity. This guy is most of the time less than 1. So we expect the limit will be 0. Okay. Let's check how they agree in between. Okay. So this is of the form indeterminate form 1 to infinity. So again, we use the usual procedure. This is cosine x to the power 1 over x squared. Okay. Then ln y is equal to 1 over x squared ln cosine x. And here we must stop and check if ln cosine x makes sense. When x is close to 0, whether x is positive or negative, cosine x is close to 1. So it's always positive there. So around x equals 0, ln cosine x makes sense. We are taking the logarithm of a positive function. Okay. Now when x goes to 0, ln cosine x goes to 0, divided by x going to 0. So this is already in this form, ln cosine x over x squared. Okay. So when you take the limit, this is an indeterminate. This will give you an indeterminate limit of the form 0 over 0. So we take limit as x goes to 0 of ln y, which is limit x goes to 0 of ln cosine x over x squared. Okay, so this is an indeterminate form. So we hit it with L'Hopital. Limit x goes to 0 of 1 over cosine x. Okay, we'll take one more derivative. Okay, so okay, let's see. I wanted to write secant x. I'll write it in the next step. Cosine x times the derivative of cosine x, which is minus sine x, over 2x. Okay, so now we look at this. This is again 0 over 0. We can hit this with the L'Hopital, but we have other techniques also. We notice that this guy here, 1 over cosine x, is not doing us any harm. It's not killing anybody. It's not 0. So we can take it out. Okay. On the other hand, I have sine x over x. I already know the answer to this. So I can write this as limit x goes to 0 of minus secant x, 1 over cosine x over 2, okay, times limit x goes to 0 of sine x over x. I know the limit of this. Well, this limit is no problem. So the answer is minus 1 over 2, right? Equals minus 1 over 2. Okay, so what did we find? We found that this thing was ln of limit as x goes to 0 of y. So this thing is equal to minus 1 over 2. Okay, so it tells me that limit of y as x goes to 0 is e to the power minus 1 over 2. Okay, so they fought, they were fighting, and they came to an agreement at a very interesting point in between. Okay, so let me do one more funny thing and then there is always this classical thing that I'm sure you learned when you learned logarithm. So find limit x goes to 0 of x to the power 1 over ln x. Okay? So you remember this, ln x goes to infinity. So this is of indeterminate of the form 0 to 0. Okay, so did you see this in kindergarten? Okay, so these things are done in kindergarten because this thing is a constant. Okay, so you let y equals x to the 1 over ln x. Okay, ln y is equal to 1 over ln x ln x. Okay, so this is 1. This is identically 1. Okay, right? So y equals e. Okay. So where did I write this thing? Oh. Okay, so we are taking, so it turns out that there is no indeterminacy here, right? We are taking the limit of e as x goes to somewhere, okay? So this is equal to limit as x goes to 0 of e, so the limit is e. Everyone agree? Okay, so you should have seen this in kindergarten. Okay, there is another interesting thing. Limit as x goes to, in this case, 0 from the right, because certain things will, well, because I'm taking ln x, 1 over x plus ln x. When x is going to 0, this becomes plus infinite. We are going to 0 from the right. This becomes plus infinite. This becomes minus infinite. So they are fighting. Okay. So this is of the form infinite minus infinite. It doesn't make sense because it depends on who is going to infinity faster, and if the other guy is showing any resistance, etc. So that is what we will find. Okay. So we can consider this as plot the graph of y equals 1 over x plus ln x when x is positive. Okay. So when we are plotting this, of course, you are interested in what happens when you approach to the domain. Here the domain is 0, infinity. So in between, we'll be able to predict the behavior of this because we'll take derivative, second derivative, we'll know concavity, minimum, maximum, etc. But what happens when you approach the limit here and here? Okay, so we calculate this y equals 1 over x plus ln x. So I think I'll simplify this. This is 1 plus x ln x over x. Okay, so here when we take the limit, there is no indeterminacy, right, suddenly. Because we know that x ln x, there is the indeterminacy here, but we resolve this once and for all. You don't have to do it all the time. X polynomials always beat logarithms. Okay, so if x goes to 0, this goes to 0. This whole thing goes to 0. So the numerator goes to 1, the denominator goes to 0, so the limit is infinite. Okay? So limit as x goes to 0 from the right of y is equal to infinite. Okay? Limit x goes to 0 from the right, 1 plus x ln x is equal to 1. The other limit, how about the other limit? Limit of y as x goes to infinity. As x goes to infinity, there is no, again, fighting. This goes to 0, this goes to infinite. Okay, so the limit is infinite. So if we are plotting the graph, we'll look at y prime and we'll look at y double prime. Okay, so people started to talk outside, so let me just write the limits here. So this is x minus 1 over x squared, and second derivative is 2 minus x over x cubed. Okay, so this says that the derivative is negative before 1, so the function is decreasing, well, which makes sense because the function was infinite at 0. So from being asymptotic to infinity to the y-axis, it goes down up to the point x equals 1, and then it is positive, then it increases, it goes to infinity. But when I say it increases, it's not increasing like this, it's increasing like logarithm, so it's increasing like this. Okay, so somewhere at the edge of the universe, it will be slightly high. Okay, but we look at this one. So what you expect is that the curve is coming down, it is going up, but it doesn't go like this, it is very small. When x is very large, this part is negligible. The graph must be like ln x, and ln x is concave down. So somewhere in between, the concavity must change. So this is saying that the concavity changes at x equals 2. Okay? So looking at this thing, we can draw the graph like this. So the function comes like this, goes up, and then it's like this. Okay? So somewhere here, the concavity changes. So this is 2. So this is the minimum point. Okay, so this is y-axis, this is x-axis, and this is y equals 1 over x plus ln x. So when x equals 1, 1 over 1 plus ln 1, so this is 1. Okay, so we used everything we learned so far, and we managed to plot the graph of this. Okay, so I had an interesting problem for you, but time is up, so bad luck.